The human eye that enables us to view is a very complex organ. Let us first study its structure. The white protective membrane that is seen when looked at the eye directly is called the sclera. It is a tough, opaque, fibrous outer layer of the eyeball. The circular colored part is called the iris. The color of the eye is determined by the color of the iris. The central transparent area of the iris is called the pupil. The iris works like the shutter of a camera. It absorbs most of the light that falls on it and allows a part of it to pass through the pupil. The amount of light that enters the inner parts of the eye depends on the size of the pupil, which is controlled by the muscles present in the iris. In bright light, the iris contracts the pupil to restrict the light, whereas in dim light, it widens the pupil to admit more light into the eye. The eyeball that contains different parts of the eye is roughly spherical in shape with a diameter of 2.5 centimeter. A transparent protective membrane called the cornea covers the small bulged portion at the front of the eyeball. In fact, the iris and the pupil lie behind the cornea. The crystalline lens and the retina are some of the other important parts of the eye behind the cornea. The crystalline lens is held in its position by the ciliary muscles. The retina is a film of nerve fibers covering the curved back surface of the eye. It detects the presence of light and its color and sends this information to the brain through the optic nerve for further processing. The retina is able to detect the light and its color because of the presence of sensors called rods and cones. The rods are sensitive to low light, whereas the cones, which require a greater intensity of light, are sensitive to color. The portion between the cornea and the lens is filled with a watery fluid called the aqueous humor. The space between the lens and the retina is filled with a jelly-like fluid called the vitreous humor. Now let us study the working of the human eye. Light entering the eye is first refracted by the cornea. The refractive power of the cornea is large and fixed. The refracted light is then incident on the iris. The crystalline lens is just behind the iris, and light after passing through the pupil falls on it and is again refracted to form a sharp image on the retina. For an object to be seen clearly, the image must be formed exactly on the retina. The crystalline lens along with the cornea is able to refract the light that enters the eye to form a sharp image on the retina. The eye is able to focus objects at different distances sharply on the retina by changing the focal length of the crystalline lens. The process of adjusting to different object distances by changing the focal length of the crystalline lens is known as accommodation. Ciliary muscles help in adjusting the focal length of the crystalline lens. Ciliary muscles are in relaxed state when an object at infinity is sharply focused on the retina. In this case, the focal length of the crystalline lens is the maximum and is equal to the diameter of the eye. When the object is close to the eye, the tension in the ciliary muscles increases and the lens becomes more bulged with reduced radii of curvature. The reduction in the radii of curvature of the crystalline lens reduces its focal length also. But the focal length of the crystalline lens cannot be reduced beyond a limit. Hence, there is a limit for the closest distance for which the lens can focus light on the retina. This is called the least distance of distinct vision, or near point, represented by the letter D. Usually the value of D is taken as 25 cm for a normal eye. The greatest distance for which the lens of a relaxed eye can focus light on the retina is called the far point. The far point of a normal eye is at infinity. We can summarize the three important functions of the eye as follows: admitting appropriate amount of light, refracting the light to form a sharp image, collecting and sending information about the image to the brain for further processing. Now let us discuss some common optical defects in the human eye. The most common defect of the human eye that is found in aged persons is presbyopia. The ability to focus on near objects diminishes with age. This is known as presbyopia. The near point changes with age. For a 10-year-old boy with good health, the near point may be about 7 to 8 cm. This changes with age and may even reach 2 meters for an old person of the age of 60 years. Hence, aged people cannot see objects placed at normal distances of about 25 cm. The incoming light rays are refracted to focus behind the retina. Presbyopia can be corrected by using an appropriate converging lens. Another vision defect that is similar to presbyopia is hypermetropia, or farsightedness. Note that presbyopia is caused by old age, whereas hypermetropia is a vision defect that can be observed in persons of any age. A person suffering from hypermetropia will have normal vision when looking at objects at the far point. But the objects that are close to the eye are focused behind the retina, and as a result, vision is blurred. The defect caused by hypermetropia can be rectified by using a convex lens of appropriate focal length. When a converging lens of suitable focal length is used to rectify either presbyopia or hypermetropia, the image of the object is formed at the near point of the person. For example, let us find the power of the corrective lens used by a person suffering from hypermetropia with near point at 2 meters. Given that the near point of the person is 2 meters, but for a normal person the near point is 0.25 meters. In case of the person suffering from hypermetropia, an object placed at 0.25 meters is focused behind the retina. If a corrective lens is used, it must form the image at a distance of 2 meters. This image will act as an object for the eye lens. That means if U is equal to 0.25 meters, then V must be equal to 2 meters. Substituting these values in the lens formula and solving for the optical power, we get power P is equal to 3.5 diopter. Another commonly observed eye defect is myopia or nearsightedness. An optical defect in which distant objects appear blurred because their images are focused in front of the retina is called myopia or nearsightedness. The person suffering from myopia will have perfect vision when looking at objects close to the eye. But in the case of an object at a faraway place, the eye produces more than required convergence, and as a result, the image is formed before the retina. The effects of myopia can be reduced by using a concave lens of suitable focal length. A defect of vision caused when the cornea is not spherical in shape is called astigmatism. Because of the non-spherical cornea, the eye lens will have different curvatures in different planes. Light in one plane is focused properly on the retina, and objects in that plane are visible clearly. Light from a perpendicular plane is focused at a different location other than the retina, resulting in blurred view of the objects lying in that plane. Hence, a person suffering from astigmatism cannot see all directions equally well. Astigmatism can be corrected by using a cylindrical lens of desired radius of curvature with an appropriately directed axis. We know that light rays, when incident on a lens, converge in the case of a convex lens and diverge in the case of a concave lens. The degree of convergence or divergence depends on the focal length of the lens. If the focal length of a lens is small, then the convergence or the divergence of light is more. On the other hand, if the focal length of the lens is high, then the convergence or the divergence is less. The physical quantity, that is a measure of the convergence or divergence of light introduced by a lens, is called its optical power. The optical power of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at a unit distance from the optical center. You know that a light ray, when incident parallel to the principal axis, after refraction by a convex lens, passes through its principal focus. If the ray is incident at a height h from the pole, and the deviation of the light ray or the angle through which the light ray converges is d, then tan d is equal to h by f. If h is equal to 1 unit, tan d is equal to 1 by f. But as per definition, tan d for h equal to 1 unit is the power of the lens. Therefore, optical power P is equal to 1 by f. That means optical power of a lens is the reciprocal of its focal length. The SI unit of optical power of a lens is dioptra and is indicated by D. Power of lens is 1 dioptra if its focal length is 1 meter. Power of a lens can be positive or negative. As per the Cartesian sign conventions, focal length of a convex lens is positive and that of a concave lens is negative. Hence, the power of a lens is positive for a converging lens and negative for a diverging lens. Note that the focal length and hence the optical power of a lens depends on the medium in which the lens is placed. For example, a converging lens in air with focal length equal to 20 cm is made of glass of refractive index 3 by 2. Let us find its optical power when placed in water of refractive index 4 by 3. It is given that refractive index of glass Ng is equal to 3/2. Focal length of the lens in air f equal to 20 cm or 1/5 meter. According to the lens maker's formula, 1/f is equal to Ng minus 1 into 1/r1 minus 1/r2. Substituting the values of f and Ng in the equation and on further simplification, we get 1/r1 minus 1/r2 is equal to 10 per meter. Let the focal length be f dash when the lens is placed in water. Then, according to the lens maker's formula, 1/f dash is equal to Ng/Nw minus 1 into 1/r1 minus 1/r2. On substituting the above values and on further simplification, we get 1/f dash is equal to 1.25 per meter. That means the power of the lens in water is equal to 1.25 dioptra. Therefore, the optical power of the given lens in air is 5 dioptra, and when placed in water, it is changed to 1.25 dioptra. Many optical instruments use a system of combination of lenses in order to get the required magnification and to enhance the sharpness of the picture. Let us now derive an expression for the effective focal length of a combination of two thin lenses A and B with focal lengths FA and FB placed in contact with each other coaxially. Let a point object O be placed at a distance u from the first lens A. Since we deal with thin lenses, all distances can be measured from the contact point of both the lenses, S. This is because, in such a situation, the optic centers of the two lenses will coincide with S. If there were only one lens, A, the image of the point object O would have formed at I'. Let the distance of the image be V1. Using the thin lens formula, we can write that 1/FA is equal to 1/V1 minus 1/U. Let this be equation 1. If the presence of the second lens is also considered, the final image will not be formed at I'. Let us analyze the refraction through the second lens. If a diverging beam of light is incident on a lens, then the object is a real object. On the other hand, if a converging beam of light is incident, then it is treated as a virtual object. Hence, for the second lens, I' acts as a virtual object. The ray of light is further converged to form an image at I. If the image I is at a distance V, then 1/FB is equal to 1/V minus 1/V1. Let this be equation 2. By adding equations 1 and 2, we get 1/FA plus 1/FB is equal to 1/V minus 1/U. Let this be equation 3. For the system of two thin lenses in contact, U is the object distance and V is the image distance. If F is the effective focal length of the lens system, then using the thin lens formula, we can write that 1 by F is equal to 1 by V minus 1 by U. Let this be equation 4. From equations 3 and 4, we can write that 1 by F is equal to 1 by FA plus 1 by FB. Let this be equation 5. Since optical power of a lens is the reciprocal of its focal length, we can rewrite the equation 5 in terms of the optical powers as P is equal to PA plus PB. Let this be equation 6, where P is the net optical power of the combination of two lenses with individual powers equal to PA and PB. For a system of n lenses in contact, we can write equations 5 and 6 as 1 by F is equal to 1 by F1 plus 1 by F2 plus so on up to plus 1 by Fn, and P is equal to P1 plus P2 plus so on up to plus Pn. In case of a system of lenses, the image formed by one lens is the object for the next lens. Hence, the total magnification of the combination is a product of the magnifications of the individual lenses. If the magnification of the combination is M and the magnification of the individual lenses are M1, M2 and so on up to Mn, then M is equal to M1 into M2 into so on up to Mn. While using these equations, it is important to note that proper sign convention is to be applied for the values of focal length and optical power. Let us look at an example to understand this better. If a convex lens of focal length 10 cm is in contact with a concave lens of focal length 15 cm, how does the combination work? According to the Cartesian sign conventions, we have focal length of the convex lens f1 equal to 10 cm and the focal length of the concave lens f2 equal to minus 15 cm. If f is the focal length of the combination, then 1 by f is equal to 1 by f1 plus 1 by f2. Substituting the values of f1 and f2 and after simplification, we get f is equal to 30 cm. Since the effective focal length is positive, the combination of the given lenses act as a convex lens of focal length 30 cm. If these two lenses are separated by a distance of 10 cm and a point object is placed at a distance of 15 cm before the convex lens, where does the final image get formed? In this case, in addition to the focal lengths of the two lenses, it is also given that the distance between the two lenses, d, is equal to 10 cm and the object is at a distance of 15 cm. First, let us find the position of the image I1 formed by the convex lens only. Let the image distance be V1. On substituting these values in the thin lens formula and solving for V1, we get V1 equal to 30 cm. Hence, the image is formed at a distance of 30 cm from the convex lens. Now introduce the concave lens between the convex lens and the image I1 at a distance of 10 cm from the convex lens. The image I1 formed by the first lens serves as the object for the second. This distance U1 is 20 cm to the right of the concave lens. Since it is to the right of the lens, its value is positive. If the final image is at a distance V from the concave lens, then 1 by V is equal to 1 by F2 plus 1 by U1, or V is equal to U1 F2 by U1 plus F2. On substituting the values of U1 and F2 and solving for V, we get V as equal to minus 60 cm. The negative sign indicates that the final image is formed to the left of the concave lens at a distance of 60 cm. Note that the virtual object is in between F and 2F of the concave lens, and hence the rays are diverged to form an image to the left of it. Lens is a transparent material bound by two surfaces, of which at least one is spherical. Lenses are classified based on the curvature of the spherical surfaces. Two of the most useful lenses are the double convex lens and the double concave lens. If both the surfaces are convex, the lens is called a double convex or a biconvex lens. And on the other hand, if both the surfaces are concave, then the lens is a double concave or a biconcave lens. The central point of a lens is called its optical center. Since there are two spherical surfaces, a double convex lens or a double concave lens has two centers of curvatures. C1 is the center of curvature corresponding to the first curved surface having radius of curvature R1. C2 is the center of curvature corresponding to the second curved surface having radius of curvature R2. The straight line joining C1 and C2 is the principal axis of the lens. If the thickness of the lens is very small compared to other measurements, such as object distance or image distance, etc., it is called a thin lens. A ray of light incident on a double convex lens or a double concave lens undergoes refraction at each of the spherical surfaces. In case of a double convex lens placed in air, the light ray bends towards the normal, C1N1, at the first spherical surface, and bends away from the normal, C2N2, at the second surface. Paraxial rays parallel to the principal axis incident on a double convex lens, upon refraction, converge to a point on the principal axis. This is called the second principal focus of the lens. Principal focus towards the source of light is called the first principal focus of the lens. In case of a double concave lens, the incident ray bends towards the normal, C1N1, at the first interface, and away from the normal, C2N2, at the second interface. when a parallel beam of light rays is incident on a double concave lens. Upon refraction, it appears to be diverging from a point on the principal axis, and such a point is called the second principal focus. Note that if we merely mention principal focus, it means we are referring to the second principal focus. The distance between the optical center and the principal focus is called the focal length f of the lens. Let us now study the images of an extended body formed by a lens. To locate the image by drawing a ray diagram, we usually trace the path of any two of the following rays. Light ray that is parallel to the principal axis, after refraction, passes through the second principal focus in case of a double convex lens, and appears to diverge from the second principal focus in case of a concave lens. If a light ray is directed towards the optical center of a lens, then it passes through the lens without any deviation. If a light ray passes through the first principal focus of a convex lens, then after refraction it passes parallel to its principal axis. In case of a double concave lens, if a ray of light appears to converge onto the first focal point, then after refraction it becomes parallel to its principal axis. Now, observe the image formation in case of a convex lens when an extended object is placed at different positions. In the case of a double concave lens, the image formation for various positions of the object is as shown. Observe that the double concave lens always forms a diminished virtual image, and as the object is moved towards the lens, the image also moves in the same direction. The images formed by a lens can also be explained mathematically as follows. Consider a double convex lens AB made of material with refractive index N2 and placed in a medium of refractive index N1. Let C1 and C2 be the centers of curvatures of the two spherical surfaces ADB and AEB with their radii of curvature equal to R1 and R2 respectively. If a point object O is placed on the principal axis, its image is formed at I. Let U be the object distance and V be the image distance. The refraction of light through the lens can be split into two steps. In the first step, let us consider the refraction at the first spherical surface ADB. Because of this refraction, a real image of O would have formed in the second medium at I1. According to the Cartesian sign convention applicable for refraction at spherical surfaces, measurements are taken from the intersecting point of the spherical surface and the principal axis. Let DI1 be V'. Since we consider only thin lenses, DO is equal to U. We know that the relation between object distance U and image distance V for the refraction at a spherical surface is given as N2 by V minus N1 by U equal to N2 minus N1 by R, where R is the radius of curvature for the curved surface. Using this, we can write that N2 by V' minus N1 by U is equal to N2 minus N1 by R1. Let this be equation 1. In the second step, let us consider the refraction at the second spherical surface AEB. Because of the refraction at AEB, the image is actually formed at I instead of forming at I1. Since the lens we are dealing with is a thin lens, we can write that EI is equal to V and EI1 is equal to V dash. Hence, we can write N1 by V minus N2 by V dash is equal to N1 minus N2 by R2. Let this be equation 2. On adding equations 1 and 2, we get N1 into 1 by V minus 1 by U is equal to N2 minus N1 into 1 by R1 minus 1 by R2. This can be written as 1 by V minus 1 by U is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. Since N21 is the refractive index of the second medium with respect to the first medium and is equal to N2 by N1, we can write 1 by V minus 1 by U is equal to N21 minus 1 into 1 by R1 minus 1 by R2. Let this be equation 3. If the object is at infinity, the image will be formed at the second principal focus. That means, if U is equal to infinity, then V is equal to focal length f. Therefore, equation 3 can be written as 1 by f is equal to N21 minus 1 into 1 by R1 minus 1 by R2. Let this be equation 4. This equation is known as lens maker's formula. If we observe equations 3 and 4, the right side of both the equations are identical. Hence, we can equate the terms on the left. Doing so, we get 1 by f is equal to 1 by V minus 1 by U. This equation is known as thin lens formula. Now place an object OJ of height h before a double convex lens. Let IG be its image and of height h dash. Since the two triangles POJ and PIG are similar triangles, we can write that IG by OJ is equal to PI by PO. But IG is equal to minus h dash. OJ is equal to h. PI is equal to V. And PO is equal to minus U. On substituting these values in the above equation, we get h dash by h is equal to V by U. But linear magnification M is equal to h dash by h. Therefore, in case of a thin lens, the linear magnification M is equal to V by U. Lens maker's formula is useful in calculating the required curvatures to make a lens of desired focal length. Note that N21 is the refractive index of the material of the lens with respect to the refractive index of the medium in which it is placed. R1 is the radius of curvature of the first spherical surface on which the light ray is incident, and R2 is the radius of curvature of the second spherical surface. It is also very important to apply proper sign conventions. Let us apply the lens maker's formula to find out the focal length of a double concave lens of glass of refractive index 1.5 placed in air and with radii of curvature 30 cm and 45 cm respectively. It is given that N2 is equal to 1.5, N1 is equal to 1, R1 is equal to minus 30 cm and R2 is equal to 45 cm. Note that since R1 is measured in the direction opposite to that of the incident ray, it is taken with a negative sign. Substituting these values in the lens maker's formula and on further simplification, we get F is equal to minus 36 cm. What happens if the lens is placed in a liquid of refractive index 1.75? Now, N1 is equal to 1.75 and all other values remain same. Substituting these values in the lens maker's formula and on further simplification, we get F is equal to 126 cm. Note that the focal length is positive. This means that a double concave lens placed in a tensor medium acts as a converging lens. Let us now look at the sign conventions we follow in case of lenses. These are similar to the ones we followed in case of spherical mirrors. All measurements are made from the optical center of the lens. Measurements made in the direction of the incident light are taken as positive, and if measured in the opposite direction, they are taken as negative. Heights in the upward direction to the principal axis are taken as positive, and in the downward direction are taken as negative. Note that the focal length is positive for a double convex lens and negative for a double concave lens. Let us see how we apply sign conventions by solving the following example. Where should an object be placed before a convex lens of focal length 10 cm to get an image that is 3 times the size of the object? In this problem, it is given that F is equal to 10 cm and M is equal to 3. M is positive if the image is erect and negative if the image is inverted. As per the thin lens formula, 1 by F is equal to 1 by V minus 1 by U. On rearranging the terms, we get V by U is equal to F by U plus F. Therefore, linear magnification M is equal to V by U which is also equal to f by u plus f. If the image is real, then minus 3 is equal to 10 by u plus 10. On simplification, we get u is equal to minus 40 by 3. If the image is virtual, then m is equal to 3. Substitute these values in the above equation, and on further simplification, we get u is equal to minus 20 by 3. A prism is an optical apparatus made of transparent material with flat and polished surfaces that refract light. The most commonly used prism is a triangular prism which has 2 triangular and 3 rectangular surfaces. The 2 rectangular surfaces through which light is refracted are called the refracting surfaces of the prism. The cross-section of a prism that is perpendicular to the refracting surfaces is called its principal section. Here, ABC is the principal section. The faces AB and AC represent the 2 refracting surfaces. The angle between the 2 refracting surfaces is called the angle of the prism or the refracting angle. Let us derive the expression for angle of deviation for triangular prism. Consider a light ray PQ incident on the refracting surface AB at an angle of incidence I. Let NN' be the normal to the surface AB at Q. The ray of light refracts at the face AB and QR represents the refracted ray. Let the angle of refraction be R1. The refracted ray QR is incident on the refracting surface AC at R and emerges along RS from the prism. Let NN' be the normal to the surface AC at R. For refraction at the surface AC, let the angle of incidence be R2 and angle of refraction be E, which is also known as angle of emergence. The angle between the incident ray PQ and the emergent ray RS is called angle of deviation D. In the quadrilateral AQNR, angles AQN and ARN are right angles. Hence, angle A plus angle QNR is equal to 180 degrees. Let this be equation 1. Since the sum of the angles in a triangle is equal to 180 degrees, in the triangle QRN, R1 plus R2 plus angle QNR is equal to 180 degrees. Let this be equation 2. From equations 1 and 2, we can write that angle A is equal to R1 plus R2. Since angle A is the refracting angle of the prism, we can write that refracting angle A is equal to R1 plus R2. Let this be equation 3. In the triangle MQR, angle MQR is equal to I minus R1 and angle MRQ is equal to E minus R2. Since in a triangle, external angle is equal to the sum of the 2 opposite internal angles, for the triangle MQR, we have D is equal to I minus R1 plus E minus R2, or D is equal to I plus E minus of R1 plus R2. On substituting the value of angle A from equation 3, we get D is equal to I plus E minus A. Let this be equation 4. Since the angle of refraction depends on the wavelength and refractive index of the prism, we can say that the angle of deviation D depends on the refractive index of the prism, wavelength of the incident light ray, refracting angle of the prism, and the angle of incidence. The angle of deviation increases with increase in the refractive index of the material of the prism. more the wavelength of the incident light ray, less is its deviation. Experimentally, it has been found that the angle of deviation decreases with increasing refracting angle. If the variation of the angle of deviation is plotted against the angle of incidence, the graph is as shown. As the angle of incidence increases, the angle of deviation initially decreases, reaches a minimum value, and then increases. The minimum value of deviation is represented by dm and is known as the angle of minimum deviation. Hence, corresponding to any value of the angle of deviation other than dm, we have two angles of incidence. These two angles correspond to I and A. That means, if one is the angle of incidence, the other will be the angle of emergence. Interchanging I and E does not make any difference to the value of deviation d. If PQ is the incident ray, then RS is the emergent ray, and if light enters the prism along SR, it emerges from the prism along QP. If the incident light strikes the prism at an angle that makes the deviation minimum, then the prism is said to be at its minimum deviation position. When the prism is placed at its minimum deviation position, it is found that the light ray passes through the prism symmetrically and is parallel to the base. In this case, the angle of incidence, I, is equal to the angle of emergence, E. Because of the symmetry, we can also write that R1 is equal to R2 and let them be equal to R. Hence, when the prism is at its minimum deviation, equation 3 can be written as A is equal to 2R or R is equal to A by 2. Equation 4 can be written as dm is equal to 2I minus A or I is equal to A plus dm by 2. But the refractive index of the material of the prism, N21, is equal to sin I by sin R. On substituting the values of I and R from equations 5 and 6, we get N21 is equal to sin A plus dm by 2 by sin A by 2. Let this be equation 7. Using equation 7, the refractive index of the material of the prism with respect to the surrounding medium can be found accurately. In this method, the values of A and dm are found experimentally. If the refracting angle of the prism is small, then the value of the minimum deviation is also small. But we know that for small angles of theta, sin theta is approximately equal to theta. Hence, we can assume that sin A plus dm by 2 is approximately equal to A plus dm by 2, and sin A by 2 is approximately equal to A by 2. Substituting these values in equation 7, we get N21 is equal to A plus dm by 2 by A by 2. On simplification, we get dm is equal to A into N21 minus 1. Therefore, for prisms of small refracting angles, minimum deviation is small and is independent of the angle of incidence. Let us apply these formulae and solve some examples. Example 1. A ray of light incident at an angle of 50 degrees is refracted through a prism at the minimum deviation position. If the angle of the prism is 60 degrees, find the angle of minimum deviation and the refractive index of the prism. In this problem, it is given that I is equal to 50 degrees, A is equal to 60 degrees. The prism is at its minimum deviation position. We know that deviation D is equal to I plus E minus A. When the prism is at minimum deviation, dm is equal to 2I minus A. On substituting the values of I and A, we get the minimum deviation equal to 40 degrees. Substituting the values of A and dm in equation 7 and on further simplification, we get the refractive index equal to 1.532. Example 2. A prism of refracting angle of 60 degrees made of glass of refractive index 3/2 is immersed in water of refractive index 4/3. Find the angle of minimum deviation for a light ray passing through the prism. In this problem, it is given that refracting angle A is equal to 60 degrees. Refractive index of glass Ng is equal to 3/2. Refractive index of water Nw is equal to 4/3. As per equation 7, N21 is equal to sine A plus dm by 2 by sine A by 2. Since the prism is in water, Ngw is equal to Ng by Nw. On substituting the respective values, we get 3/2 by 4/3 is equal to sine 60 plus dm by 2 by sine 60 by 2. On simplification, we get dm is equal to 8.46 degrees. Observe the coin placed in an empty container. Rays from the coin enter the eye and make it visible. If the eye is lowered at some point, we lose sight of the coin. As water is filled in the container, the coin is visible again. This is due to refraction of light. Some of the rays of light from the coin, while traveling from water to air, bend at the water-air interface and reach the eye. This makes the coin visible again by giving the impression that the object is at a different location. While passing from one transparent medium to another, an obliquely incident ray of light bends at the interface of the two media. This phenomenon is called refraction of light. Refraction of light is due to the fact that the speed of light is different in different media. The extent of refraction can be found if we know an optical property of the medium called refractive index. Refractive index or absolute refractive index N of a medium is defined as the ratio of the speed of light in a vacuum to its speed in the medium. It is a pure number with no units and dimensions. If the speed of light in a medium is v, then n is equal to c by v. Let this be equation 1. Note that the speed of light in a medium is inversely proportional to its refractive index. For example, the refractive index of water Nw is 1.33 and that of the glass Ng is 1.52. Since refractive index of glass is more than that of water, the speed of light in glass is less than the speed of light in water. If the refractive index of a medium is greater than that of another medium, then the first medium is said to be optically denser than the second medium. For example, glass is optically denser than water. Note that optical density of a medium is different from its mass density. The optical density of a medium is its refractive index and depends on the speed of light in it. Whereas mass density is the mass per unit volume. When light travels from denser medium to a rarer medium, its speed increases and bends away from the normal. On the other hand, if light travels from a rarer medium to a denser medium, its speed decreases and bends towards the normal. The relationship between the angle of incidence, I, and the angle of refraction, R, is explained by the laws of refraction. When light travels from medium 1 to medium 2, 1. The incident ray, the refracted ray, and the normal to the interface at the point of incidence all lie in the same plane. 2. For a given pair of media, the ratio of sine of the angle of incidence to sine of the angle of refraction is a constant. This can be written as sine I by sine R is constant and is known as Snell's law. The constant in this equation is called the refractive index of the second medium with respect to the first medium, and is denoted by N21. N21 is a characteristic of the pair of media for a given wavelength of light and is equal to the ratio of the speed of light in medium 1, V1, to the speed of light in medium 2, V2. Let this be equation 2. By using equation 1, we can write N1 is equal to C by V1 and N2 is equal to C by V2. Therefore, V1 by V2 is equal to N2 by N1. Using equation 2, N21 is equal to V1 by V2, which is equal to N2 by N1. If N12 is the refractive index of the medium 1 with respect to medium 2, we can write that N12 is equal to V2 by V1. From these two equations, we can conclude that N21 is equal to 1 by N12. Now, consider a case where a ray of light first travels from medium 1 to medium 2, and then from medium 2 to medium 3. Let N21 be the refractive index of medium 2 with respect to medium 1. N3, 2, be the refractive index of medium 3 with respect to medium 2. And N3, 1, be the refractive index of medium 3 with respect to medium 1. If V1, V2, and V3 are the speeds of light in the three media respectively, then we have N21 is equal to V1 by V2. N32 is equal to V2 by V3. And N31 is equal to V1 by V3. V1 by V3 can also be written as V2 by V3 into V1 by V2. Therefore, N31 is equal to N32 into N21. The microscope is an optical instrument used to view objects of very small sizes. The apparent size of the object viewed through the microscope is many times larger than its actual size. Primarily, the apparent size of an object is determined by the size of its image on the retina, which in turn depends on the angle subtended by the object at the eye. When the object is far from the eye, it subtends a small angle at the eye, and hence its apparent size is also small. As it is moved closer to the eye, the angle subtended by it at the eye increases, resulting in the increase of its apparent size. We know that the closest distance for comfortable view is the least distance of distinct vision, or the near point, usually represented by D. When the object is placed at the near point, the angle subtended by it at the eye and its apparent size is the greatest. If the object is closer to the eye than the near point, the eye cannot focus its sharp image on the retina. But a simple microscope or magnifier can be used to view such objects without any strain on the eye. A simple microscope is a converging lens of a small focal length. If it is placed between the eye and the object such that the object distance u is less than its focal length, then the erected magnified virtual image of the object is formed beyond the near point. The angular magnification, or the magnifying power of a simple microscope, is the ratio of the angle subtended by the image at the eye when seen through the microscope to the angle subtended by the object at the unaided eye when it is placed at the near point. If theta is the angle subtended by the image at the eye when the object is seen through the simple microscope, and theta naught is the angle subtended by the object at the eye when placed at the near point, then the angular magnification, or the magnifying power m, is equal to theta by theta naught. Now, Let us find some useful expressions for the magnification of a simple microscope. If the height of the object is h, then tan theta naught is equal to h by d. But for small angles, tan theta naught is approximately equal to theta naught. Hence, we can write that theta naught is equal to h by d. Let this be equation 1. When the object is viewed through a simple microscope, the angle subtended by the image is the maximum when it is formed at the near point, and minimum when it is formed at infinity. When a simple microscope is adjusted in such a way that the object is at a distance slightly less than the focal length of the lens, then the virtual image is formed almost at infinity. This situation is known as normal adjustment. When the simple microscope is set for normal adjustment and the angle subtended by the image at the eye is theta 1, then tan theta 1 is equal to h by f, or theta 1 is equal to h by f. Let this be equation 2. If the angular magnification of the simple microscope when the image is formed at infinity is mi, then mi is equal to theta 1 by theta naught. On substituting the values of theta naught and theta 1 from equations 1 and 2, and on further simplification, we get the angular magnification or the magnifying power of the simple microscope as mi is equal to d by f. Let this be equation 3. Now let us find the angular magnification of the simple microscope when the image is formed at the near point. Let the angle subtended at the eye by the image when formed at the near point be theta 2. From the ray diagram, we can write that theta 2 is equal to h by u0. Let this be equation 4. If mn is the angular magnification of the simple microscope when the image is formed at the near point, then mn is equal to theta 2 by theta naught. On substituting the values of theta 2 and theta naught from equations 4 and 1, and on further simplification, we get mn is equal to d by u0. Let this be equation 5. But from the lens formula, we have 1 by u is equal to 1 by v minus 1 by f. Using the Cartesian sign convention, we can write that u is equal to minus u0, v is equal to minus d. Substituting these values in the lens formula and then multiplying both sides with minus d. And on further simplification, we get d by u0 is equal to 1 plus d by f. On comparing this with equation 5, we get mn is equal to 1 plus d by f. Let this be equation 6. From equations 3 and 6, we observe that the magnifying power of the simple microscope is greater when the image is formed at the near point than when it is formed at far point. We prefer to have the final image formed at the far point because the images formed at the far point can be seen by a relaxed eye with minimum strain. when greater magnification is required to view microscopically smaller objects, a compound microscope is used. A compound microscope consists of two convex lenses arranged coaxially. The lens O, that is close to the object to be viewed, is called the objective, and the lens E, that is close to the eye, is called the eyepiece. The objective of a compound microscope is of a small focal length and has a small aperture, whereas the aperture of its eyepiece is large. Let a small object AB be placed at a distance that is just greater than the focal length of the objective FO. When the light rays from the object are incident on the objective forms an image A'(B'), which is real, inverted, and magnified. This image A'(B') acts as the object for the eyepiece. If the position of the eyepiece E is so adjusted that A'(B') lies between the optical center and the first principal focus, then a virtual and magnified final image A'(B') is formed. Let the height of the object AB be h and the height of the image A'(B') formed by the objective be h'. Let us also define the tube length L of a compound microscope as the distance between the second focal point of the objective and the first focal point of the eyepiece. If MO is the magnification due to the objective and theta is the angle that the ray refracted by the objective makes with the principal axis, then MO is equal to h' by h, and tan theta is equal to h by FO, which is also equal to h' by L. From these two equations, we get MO is equal to L by FO. Let this be equation 7. If the eyepiece is adjusted in such a way that the image A'(B') is formed between the first focus FE and the optic center of the eyepiece, and it is very close to FE, then the final image is formed at far point. Then we say that the compound microscope is set in normal adjustment. Since the eyepiece acts as a simple microscope, using equation 3, we can write the magnification due to eyepiece ME is equal to D by FE. Let this be equation 8. Since the image formed by the first lens becomes the object for the second lens, the total magnification of the combination M is the product of the magnification due to the objective and the magnification due to the eyepiece. Therefore, M is equal to MO into ME. Substituting the values of MO and ME from equations 7 and 8, we get M is equal to L by FO into D by FE. That means, when set for normal adjustment, the magnifying power of a compound microscope M is equal to L by FO into D by FE. If the eyepiece is adjusted such that the final image is formed at the near point, then, using equation 6, ME is equal to 1 plus D by FE. In such a case, the magnifying power of the compound microscope M is equal to L by FO into 1 plus D by FE. For larger magnification, the objective and the eyepiece of a compound microscope must have small focal lengths. The magnifying power is generally expressed in terms of x, where x is the number of times the size of the image appears to be when compared to the size of the object. For example, if a compound microscope is marked as 10x, then its magnification is 10, and It denotes the number of times the size of the image appears to be when compared to the size of the object. In fact, the objective and the eyepiece of a compound microscope are made of a multiple lens system. This improves the quality of the image and minimizes various optical defects. The telescope is an optical instrument that is used to view distant objects clearly. The astronomical telescope is used to view celestial bodies, and the terrestrial telescope is used to view distant objects on the Earth's surface. Let us now study about an astronomical telescope. Consisting of two converging lenses placed coaxially. One of the converging lenses is called the objective, which is closer to the object to be viewed, and the other is closer to the eye and is called the eyepiece. To capture the image of a distant object, the objective must gather large amounts of light, and hence the aperture and the focal length FO of the object is large. The eyepiece of a telescope has a small aperture and a small focal length FE. When the telescope is turned towards a celestial object, parallel rays from the distant object are incident on the objective, which form an image AB at the focus FO of the objective, and this image is real, inverted, and of point size. The image AB acts as an object for the eyepiece, and the final image A-B- of the distant object is formed by the eyepiece. The image A-B- is virtual, magnified, and is inverted with respect to the original object. Let the angle subtended by the object at the objective be alpha. Since the object is far away, the angle subtended by it at the objective is same as the angle subtended by it at the eye. Let beta be the angle subtended by the final image at the eye. The angular magnification, or the magnifying power of a telescope M, is the ratio of the angle subtended by the final image at the eye to the angle subtended by the object at the unaided eye. That means M is equal to beta by alpha. Let this be equation 1. Let us now derive an expression for the magnification of an astronomical telescope when it is set for normal adjustment. The telescope is said to be set for normal adjustment if the final image is formed at infinity. If the image AB is on the focal plane of the eyepiece, then the final image is formed at infinity. Since the two angles alpha and beta are very small, tan alpha is approximately equal to alpha, and tan beta is approximately equal to beta. But tan alpha is equal to AB by FO, and tan beta is equal to AB by FE. Hence, for small angles of alpha and beta, we can write that alpha is equal to AB by FO and beta is equal to AB by FE. Substituting the values of alpha and beta in equation 1 and on further simplification, we get m is equal to FO by FE. Let this be equation 2. Hence, we observe that the angular magnification or magnifying power of a telescope that is set for normal adjustment is the ratio of the focal length of the objective to the focal length of the eyepiece. In this case, the length of the telescope tube is equal to FO plus FE. It is important to note that the final image formed by an astronomical telescope is inverted. There is no difficulty for the viewer as most of the celestial objects are spherical in shape. If the astronomical telescope is used to view a terrestrial object, then the final image being inverted would be a cause of discomfort for the viewer. To overcome this problem, we use a terrestrial telescope which produces a final image that is erect with respect to the object. By placing a third lens, known as the inverting lens, between the objective and the eyepiece, we can get an erect final image. If the focal length of the inverting lens is f, then it is placed at a distance of 2f from the focal plane of the objective. When the telescope is turned towards a distant object on the ground, the rays from the object are incident on the objective, which form an image PQ on the focal plane of the objective. PQ is real, inverted, and diminished compared to the object. PQ now acts as an object to the inverting lens, and since this image PQ is at a distance 2f from it, the inverting lens forms an image P', which is real, inverted, and of same size as PQ. It is of importance to note that the image P', is erect with respect to the original object. The size of P', is same as that of PQ. The lens has merely made an inverted image erect. The image P', acts as an object to the eyepiece. If the object distance with respect to the eyepiece is less than its focal length, then a virtual image P', Q', is formed. The final image is erect and magnified since it creates a larger visual angle at the eye. We can adjust the position of the eyepiece such that P', Q' is formed on the focal plane of the eyepiece. Then, the final image will be formed at infinity and the telescope is said to be set for normal adjustment. The magnifying power of the terrestrial telescope, when set for normal adjustment, is also equal to the ratio of the focal length of the objective to the focal length of the eyepiece. In some of the terrestrial telescopes, a pair of inverting lenses is used to make the final image erect. The main considerations of a telescope are its light gathering power and its resolving power. Light gathering power of a telescope depends on the size of the objective. If the size of the objective is large, then it can collect more light, and as a result, fainter objects can also be observed. The resolving power of a telescope is its ability to observe two objects in very nearly the same direction distinctly. The resolving power of a telescope also depends on the diameter of the objective. So, telescopes with large objectives provide high resolution and high magnification. It is important to note that the resolving power and the magnifying power refer to different entities. For example, if a double star system is observed by an astronomical telescope with a low resolving power as well as with a low magnifying power, the final image is as shown. It is neither well resolved nor well magnified. If we use an astronomical telescope with a low resolving power but with a high magnifying power, the final image of the double star system is as shown. We observe that the image is well magnified but not well resolved. If we use an astronomical telescope with a low magnifying power but with a high resolving power, the final image of the double star system is as shown. We observe that the image is well resolved but not well magnified. If we use an astronomical telescope with a high magnifying power as well as with a high resolving power, the final image of the double star system is as shown. We observe that the image is well magnified and well resolved. The telescopes we discussed so far are refracting telescopes, which use a combination of lenses. The big lenses used in telescopes of high resolving power are heavy. Therefore, it is difficult to make and support them by the edges. It is also expensive to make large-sized refracting telescopes that are free from any kind of optical defects. For these reasons, modern telescopes are reflecting telescopes which use a concave mirror as an objective. The reflecting telescopes use an objective mirror at one end of an open tube, which reflects light back to a smaller diagonal plane mirror to bring the collected light to the eyepiece positioned at the side of the tube. Some of the advantages of reflecting telescopes are: as there is no chromatic aberration for mirrors, it is completely eliminated in reflecting telescopes. Spherical aberration can also be removed by using a parabolic objective mirror. Since a mirror weighs much less than a lens, reflecting telescopes are easy to handle mechanically. In some of the reflecting telescopes, a convex secondary mirror is used to focus the incident light onto the eyepiece. When a narrow beam of white light is incident on a prism made of transparent material, it is experimentally observed that the emergent light consists of several colors. These different colors are continuous with no sharp boundaries between them. But we can still identify 7 prominent colors in that band of colors. Another important observation is that the colors always appear in a specific sequence. This sequence of colors is violet, indigo, blue, green, yellow, orange, and red. The sequence of colors can be remembered by the acronym VIBGYOR, formed by the first letters of all the 7 colors. It was Isaac Newton who proved that these colors are already present in white light, and that the prism splits the white light into its constituent colors. In order to prove this, a similar prism was inverted and placed in the path of the emergent light rays. It was observed that different colors emerging from the first prism, on passing through the second prism, combine to form a beam of white light. Hence, it was concluded that the prism splits the white light into its component colors. The phenomenon of splitting of white light into its component colors is known as dispersion of light. The band of color components of light formed by splitting of white light is called the spectrum of light. This spectrum of colors is also known as the visible spectrum, which is a small part of the electromagnetic spectrum. Now, let us further understand the phenomenon of dispersion. We know that the color of light is related to its wavelength. If the wavelength of light is in the range of 395 to 450 nanometer, then the color of the light is violet to indigo. If the range is between 450 to 490 nanometer, the color is blue. If the range is between 490 to 560 nanometer, the color is green. If the range is between 560 to 590 nanometer, the color is yellow. If the range is between 590 to 635 nanometer, the color is orange. If the range is between 635 to 700 nanometer, the color is red. Of the 7 colors, the red color light has the longest wavelength, whereas the violet color light has the shortest wavelength. Light rays with different wavelengths travel with the same speed in vacuum or air. When all these 7 colors reach the human eye at the same time, we get the impression of white light. But in a material medium, the speed of light is different for different wavelengths. More the wavelength of a light ray, more is its speed in any given transparent material medium. That means, in a medium other than air or vacuum, the speed of red color light is the highest and the speed of violet color light is lowest. This makes the refractive index of a transparent medium different for different colors of light. A medium in which the refractive index varies with the wavelength is known as dispersive medium. Hence, light of different colors bend through different angles while passing through a dispersive medium. Normally, we don't observe the effects of dispersion when light travels through a parallel-sided glass slab. A beam of white light that enters a glass slab emerges as a white light only. But, in fact, the white light splits into its constituent colors at the first refracting surface of the glass slab. And these component colors combine to form a ray of white light while emerging out of the glass slab from the second surface without any dispersion. We can observe the effects of dispersion of light in the case of a lens, especially if the lens is thick. For example, if a beam of white light parallel to the principal axis is incident on a thick convex lens, it gets dispersed at both the edges of the lens. As a result, rays of different colors are focused at different points on the principal axis. Hence, the focal length of the lens is different for different colors. The red rays have a maximum focal length, whereas violet rays have minimum focal length. This inability of the lens to focus all the colors at one point is called chromatic aberration. Because of this, multiple colored images of an object are formed at different focal points. The image formed by violet rays is closer to the lens than the image formed by red rays. In the case of a convex lens, these images are in the direction of the incident light, and hence the chromatic aberration is positive. For a concave lens, the images formed are in the direction opposite to the incident light, and hence the chromatic aberration is negative. It is possible that a suitable combination of convex and concave lenses may be free of chromatic aberration. Such a combination of lenses used to decrease the chromatic aberration is called an achromatic doublet. Usually the two lenses used in the achromatic doublet are made of different materials, like crown glass and flint glass.